Okay, good afternoon. Welcome, everybody. Welcome to this IAS Distinguished Lecture Series. Today's speaker is Professor Sijue Wu, Robert and Lynn Brown, Professor in Science of University of Michigan. She is also a recipient of Morningside Mathematics Award twice. First time the Silver Award, and then Gold Award. So today her topic is on some last time behavior of surface water waves. Let's welcome Professor Wu.
Okay, I would like to thank Professor Chen for his invitation, and it's great to see old friends here. And I think it's very scary to talk about water waves here because you see water waves all the time, just next. And you will tell me that, okay, what you're talking about is wrong. Okay, but just do tell me that what I say is you don't believe it, okay, and or have any question, because I have 1.5 hours. Okay, okay. So what I'm going to talk about is water waves. So what we look at, so what I care about is the wave in the deep ocean. So that means in the middle of the ocean, okay, and we see the waveform. And the question is, what happens next, right? Or what are some typical behaviors there? So we have to, as a mathematician, we have to make some assumptions. So this means that I will assume that the density of the air is 0. That means I will neglect effect of the wind, okay? And I assume the density of the water is 1. And it's subject to gravity. And, okay, and also make some other assumptions. So the density of the air is 0. So keep in mind there's no wind. Oh, I'm neglecting the effect from the wind, okay? And inviscid and incompressible, we know that in the middle of the ocean, it's quite reasonable to assume it's inviscid and incompressible in such a large scale, right? And irrotational, in fact, is also quite reasonable because we are not seeing bottom and boundary, okay? So we know that rotational effects are often coming in from the boundary, but because we're far away from the boundary, and it's, we are infinite depths water and without the coast. So we're not talking about coast, okay? And so we know that if it's inviscid, and this is a basic property of the fluid dynamics, if it's irrotational initially, it stays irrotational for all time, okay? And we also assume the surface tension 0. So we know that surface tension is responsible for such small waves like ripples, okay? And in such large scale, it's reasonable to just neglect surface tension. So we care about only the behavior of the large waves, okay, not ripples, okay? Okay, so that's the basic assumption we make, okay? Okay, so that's the equation we are talking about, right? So the first is Euler equation, and density is 1, so F equal to ma. This left-hand side is the acceleration, and the right-hand side, the force term. So 0 minus g is the gravity, and p is pressure, so this pressure term, and incompressible, irrotational. And because the air density is 0, and also surface tension 0, so the pressure force from the air is just 0 along the interface. So we assume that the pressure is 0 on the interface, okay? Okay, so it is well known that when the surface tension is 0, the motion can be subject to the so-called Taylor's instability. So this Taylor's instability is governed by the so-called Taylor sign condition, okay? So basically, it says that the motion is stable if this sign is positive. So what does that mean? So this n is the normal pointing outward of the fluid. So this means the pressure has to be increasing inward in the direction of the fluid, right? And that's reasonable because otherwise, say if it's decreasing, so this means there's a force just rip open the fluid, right? And the bubble will form, and therefore this, and then of course the problem is become ill-set because you see here we assume that the fluid region is bounded by a single curve, say, or a single surface initially, and if we want to solve it, and we are assuming that this fluid domain is still bounded by a single surface, right? But if there's a hole formed inside, the topology change, and we have to reset the problem, or the problem become ill-posed. Mathematically, it says ill-posed, or actually it has ill-set, okay? So we know that, I mean, so this condition basically prevents, says that there's no bubble form, okay? Okay, so the so-called Taylor sign condition, was first introduced by G.I. Taylor in 1949, and he basically obtained by calculating the two situations, right? So if you linearize the situation that where the water is above air and the interface is almost flat, okay, and you calculate negative dP, then you will find this is negative. And we know this is an unstable situation, right? You cannot hold water above air like this, okay? And of course, if air is above water and this is a stable situation, and you calculate this quantity, it's stable, okay? But actually, what we can show is the following. So this is a work about 15 years ago. In fact, the Taylor sound condition is really not a condition. It's true always, okay? So under the assumption I'm making, like incompressible rotational, okay, and there's no surface tension and the density of the air is 0, okay. So the Taylor sound condition is really not a condition, and it holds always as long as the interface is non-self-intersecting. So that means even if we have a wave like this overturns, it's still true, okay. It is still true, so as long as the bulk of the water is below, okay. So of course this is really, I mean, this is a fact that should not be surprising to the to surfers, right? Say, for example, and that's a, sorry, okay, I want to show you a photo, right? So we know that the reason we can surf, for example, the reason we can surf, I mean, you're able to surf is because people just surf under the water, right? You can see that, I mean, the reason you can surf is because even if the wave overturns, it's stable. Otherwise, if it's all bubble underneath, you cannot surf, right? So it's just really just a fact like that. But then, of course, oh, okay, correct. Just ask me question at any time, okay? So of course, once we realize this could be something proved, actually the proof's not difficult, okay? So this gives just some simple idea. If you apply divergence to both sides of the Euler equation, you will find the following. Laplace P is negative gradient V squared. This is because, and we can see that, this is apply divergence to both sides, and divergence of Vt 0, divergence of the second term, using divergence 0, curl 0, you will find that's just gradient V squared. And the right-hand side, you get negative Laplace P, okay? It's very easy to calculate. And we also know the pressure is 0 on the interface, right? So this means that we are looking at Laplace P less than or equal to 0, so this means this P is like a subharmonic. Superharmonic. Okay, anyway, it's concave down, right? Concave down, and the pressure 0 on interface, so that means the pressure has to be increasing in the inward direction. Okay? And of course, this basic idea is using maximum principle, but in order to prove it has a strict lower bound, positive lower bound, we have to take advantage of the gravity, and also we have to put appropriate assumptions of P at infinity, right? But because I mean, this is something has to be done, right? So otherwise, the solution is artificial. So reasonable assumptions of pressure at infinity. Then you can show this is strictly positive, okay? Okay, so there are a few earlier work. So in this work of Tom Bill, Tom Ho, Rowan group, and they actually show that, say, assume you have a solution, okay? And assume this solution satisfies the Taylor sound condition. And now if you linearize the equation about this solution, and you will find that the linearized equation is well posed. So in this work, it's the importance of this sign condition is already there, right? So, but now we can actually show this is always correct. It's not a condition, okay? And so earlier, this is the first work studying the well-posedness. The so-called well-posedness means that, say, if you are given initial data, there should be a unique way to propose, there should be a unique solution for a short period of time. So this is what Nalimov showed, that for infinite depths, for 2D water wave, small data. So if initially the wave is small and the velocity is small, it remains smooth and small for a short period of time. And for Yoshihara, he's able to prove the same result by adding a bottom. But of course, adding a bottom, this finite depth the bottom has to be strictly away from the interface. Okay, so this means we are not talking about beach. The interface and the bottom intersect. Okay, if the distance is strictly positive, then the problem is also well posed. That means that for initially small and a smooth surface, it remains small and smooth for a short period of time. But of course, yes.
N is normal
Uh,
normal direction.
Yeah, N is outward normal.
So why P is pressure?
P is pressure.
C is velocity.
C is constant. It's just some constant. No. It's just saying that this has to be strictly bounded below by a positive constant. Yeah. So the pressure has to be increasing inward. Okay. So now, of course, we are able to answer this question that for any given interface, smooth interface and smooth initial velocity, even if it's big and overturned, it remains smooth for a short period of time. Okay. So for a short period of time, initially smooth interface remains smooth for a short period of time. Okay. And of course, this result has been extended to add some more odd effects. Like, for example, you can add a non-zero surface tension. We know surface tension has smoothing effect. Okay, so this is you can prove that the problem, if initially the interface, so it's a smoothing effect, and you can also add a finite depth, and this depth again has to be strictly away from the interface. Okay, so it's not talking about beach. In fact, the interface, if the interface intersects with the bottom, it's still open. Okay, so this is not studied mathematically in the regular sense. Okay, and also you can add a non-zero vorticity, but for all these work, they have to assume that the Taylor sign condition holds. So that means if the Taylor sign condition holds, or if the pressure is strictly increasing inward, then if initially the interface is smooth, it remains smooth for a short period of time. Okay, but this is crucial that the Taylor sign condition have to hold. But in fact, with these extra effect, the Taylor sign condition is not automatic. Okay, so you have to assume it in this case. Okay, so now with all these, so the question remains is, what are some large time behaviors? So we know that if initially it's smooth, it remains smooth just for some short period of time. Then what happens later? Okay, what happens later? So what happens later? So of course, what are some happens later? And okay, and in particular, we also want to know, say, what are some typical behaviors in the water wave? Okay, so this is a photo I took in San Diego. Okay, so we are very familiar with some behaviors of water wave, right? And you can just go a few steps down, and then you can see what's happening there. And this is a photo. In this photo, we can see that a lot of time, the wave surface seems to be smooth, and the small waves are nice. But then we can also see there's a wave train form, right? So the water comes in here and goes out here, and then they push together the wave train form. But we also see the wave breakings here and there, right? Okay, but this is, so what happens? Okay, so let's just start from somewhere. Okay, so this is a paragraph I took from this book, Introduction to Water Waves by G.D. Craper. So basically, this says that in most of the time, we see the wave in the open ocean have large lengths, wavelengths. Okay, so wavelength is very long. Okay. And also the height is small. The height is like 45% of time. That's no more than 1.25 meters. And 90% of time, it's no more than 6 meters in height. However, there's a record of wave of 34 meters in height, 30 meters in height. Okay. So even though most of the time we see small waves, but there are some large waves. And what's dangerous about this large wave is that it seems people believe that the large ships are damaged and disappears due to these large waves. Okay, so they say that in some part of the world, the occurrence of giant waves appears more frequent. In 1973, 2 large ships were damaged, And something similar probably accounted for the disappearance of this ship, okay? A liner, so, okay, in 1909. And no trace of her was ever found, although there had been other ships in the area at the time, including sailing ships which had not been in difficulties. So from this description, it seems that there's some dangerous wave in some localized area, right? And obviously, it's not due to storm or anything, because if it's due to storm, nearby ships should be also in trouble. Okay, so and this is like, it seems that it's in perfect clear weather, and this sailing ships nearby is fine, and nothing happened to them. But then this large ships nearby just disappeared. Okay, so what's described is the so-called rogue wave. So this is a photo. It's if you check rogue wave, you will see this photo I downloaded from internet. Okay, so this is a rogue wave, and this ship came back but damaged, but they took this picture. So it's a folklore for a long time because nobody believed it exists, because the ship damaged and disappeared, and people say, okay, well, that's because you're a bad sailor, right? It's not because any rogue wave. But then eventually the ship become better built, and they came back, and then people start to believe it. And now there's a satellite. You can see on the satellite the rogue wave actually do happen quite often. Okay, so there's a lot of study on the rogue waves. So rogue waves, by definition, are these massive large waves. Okay, and by definition, it's not caused by storms. If it's caused by storm, we can forecast it, right? So it's not so dangerous. So this, by definition, these are the waves somehow like localized and appears in perfectly clear weather without warning, and its exact cause is still not known. Okay, and there are a lot of conjectures. For example, in certain part of the world, the rogue waves seem to appear more often than the other. So the conjecture is this is because of the shape of the coastline. Certain shape of coastline has a way of something pushing the wave together and a large wave form. Okay, but in certain part of worlds, there's also like the currents and the wind. Currents going this way, the wind blow against it, and then there's a wave to push it become large. Okay, but it's not completely rule out the so-called nonlinear effect. So this is like a nonlinear Schrödinger equation, focusing effect. Even if the data is small, it could become large at a later time. Okay, so our focus for the initial, this is really the first study we have, okay, is on understanding the nonlinear effect. So the question is really that, so we really want to understand whether the nonlinearity in the water wave itself is enough to cause large wave or singularity at a later time. So we just neglect the coast, okay, the bottom, so we assume this is infinite depths, and we don't see the coast, and there's no wind, surface tension. So the question is, do waves that are initially small and smooth become large and singular at later time? Okay. Okay, so that's what we know. It's a few years now. Okay. So we focus on small and smooth data, right? Because we really see most of the time the data is small and smooth. So in this work, we are able to show that if the data is of size epsilon, so that means that this epsilon is small. Okay. So epsilon has to be sufficiently small. Mathematically, it's sufficient. Epsilon is less than epsilon 0, and we don't know what epsilon 0 is. But there is epsilon 0, so that if epsilon is less than epsilon 0, if the data is of size epsilon, so then the solution remains small and smooth for this exponential period of time. So you can see that if epsilon is very small, then the time it exists is exponentially long, right? And during this time, the wave remains small and smooth and decays with rate 1/√t. Okay, so we have to be careful. I mean, I know that there's a lot, some engineering here and the physicists here. So mathematically, we are saying this, but in reality, whether this means whether there's no rogue wave from nonlinear effect, I think it's an open question still, because we are saying epsilon needs to be less than epsilon 0, right? But in physical world, what is epsilon 0? You have to know what is epsilon 0. So there's a lot of questions remain in this respect. Okay, so we still need to get more precise information. But for the moment, we know that if the data is small, the solution remains small for exponential time. Okay? And the key idea is the following. Okay? So why we can say that the solution remains small and smooth for such a long period of time? The key idea is that, in fact, so of course, naively, we want to say, okay, we write down the equation about interface, right, or about the velocity, but then it contains nonlinearity, okay? But nonlinearity, of course, it's a nonlinear equation, of course, has quadratic nonlinearity. But however, there is a quantity of this shape, so that means if you just take the interface, y is the height, okay, the height function, and h is the so-called Hilbert transform. So if you project the height into the space of holomorphic functions in the air region. So that's exactly this quantity mean. Okay? This quantity is a projection of the height into the space of holomorphic function in the air region. If you just look at this quantity in an appropriate coordinate system, there is appropriate coordinate system so that this quantity will satisfy such an equation. And this equation, the main part, the left-hand side is completely linear and constant coefficient. And the right-hand side contains no quadratic nonlinearity. So this contains cubic and higher nonlinearity only, no quadratic nonlinearity. So remember that we are talking about small waves, small solutions. So that means no quadratic nonlinearity. The quadratic nonlinearity is of size epsilon square, right? Cubic nonlinearity is epsilon cube. So if epsilon small, the cubic nonlinearity has an effect much weaker than the quadratic nonlinearity because epsilon cube is smaller than epsilon square. Okay. So in other words, the water wave, when we look at in the right quantity, in the right coordinate system, it's more linear than we would normally imagine. Okay. So this is both right quantity and the right coordinate system allow us to say that there's no quadratic nonlinearity. In fact, the effect from the nonlinearity is weaker than we normally thought. Okay, there's no quadratic nonlinearity. Okay, so now in 3D, we also have a very similar result. Okay, so in fact, similar idea works. So for 3D, we can say a little better. So if the data is of size epsilon, this epsilon is also small, then the solution exists for all time and remains small for all time. Okay, and the wave remains small for all time and decay with rate 1/t. So why it decays with rate 1/t? Because the water wave is dispersive, right? And in 2D, in 2D means we are really looking at a cross section. Okay, in 3D is a real world situation. So the wave has one more direction to disperse out, so it decays faster. Okay, that's why it has a faster decay rate. And the key idea is really same, that when 3D water wave, when viewed through the right quantity in the right coordinate system, contains quadratic nonlinearity. No quadratic nonlinearity, sorry. Okay. So precisely that's the following. Okay. So because once we know what happens in 2D, we know what to do for 3D, right? So we try the same thing, and we look at the interface, and we take out the height component, and we project into the space of Clifford analytic function in the air region. Okay, so here is correspondingly in 3D, we also have this concept parallel the 2D that's called Clifford analytic function. Okay, so H is a Hilbert transform. Because we are talking about divergence-free, curve-free velocity, so that means it's a potential flow. That means the velocity field satisfies Laplace equation, Laplace v equal to 0. So all these concepts exist in any dimension, and then we can parallelly define the so-called Hilbert transform from the fundamental solution of the Laplacian, and then we can define this quantity, which is Clifford analytic in the space of air region, and this quantity satisfies such an equation. Okay, so the left-hand side is it's actually not as clean as a 2D. Okay, so this still contains quadratic nonlinearity, but the right-hand side only has cubic and higher order nonlinearity, so no quadratic. However, if we make the correct change of coordinate system, that means we are able to find a coordinate system so that in this new coordinate system, the left-hand side is only linear plus cubic and higher orders. Okay, so that means that in the right coordinate system, this quantity also satisfies equation that contains no quadratic nonlinearity. Okay. Okay. So now heuristically, we can see this implication of such structure. So of course, if we linearize the water wave equation naively, say if U is velocity field, and that's what we get. I mean, I just say I write down the linear part and then put nonlinear part on the right-hand side. So left-hand side looks like this. So if you just linearize straightforwardly, you will see that the nonlinear part contains quadratic nonlinear terms. Okay, and so if we can forget about the nonlinear terms, we just look at the linear part. We know that the linear equation has solution for all time, right? So if for a large class of initial data, so the linear equation is globally well posed, okay? And in 2D, so if we just this is a dispersive equation, and we know in 2D the linear part the solution decays with rate 1 over square root t. In 3D, decays with rate 1 over t. It's purely because in 3D there's one more direction to disperse out. So decay rate is faster. And now we want to understand for how long we can solve this equation, or in other words, so really precisely mathematically, the question is, so we know the linear equation can be solved for all time, right? So we want to ask, okay, for the same data that the linear equation can be solved for all time, for how long we can solve the nonlinear equation. So this basically asks the question that for how long the linear part remains dominant. Okay, so we know the nonlinear terms can cause blow up, okay, or singularities, or the solution become large. So really that we want to understand the competition between linear and the nonlinear, for how long the linear remains dominant, and we are looking at the problem in the small solution region, right? So that means that if there's a quadratic nonlinear term, then we will see that it's too big, we cannot solve for all time, okay? But if there's no quadratic nonlinearity, and the nonlinearity is of cube in high order, that means it's of size epsilon cube and smaller, then you can solve the linear part remains dominant for a longer time, and then you can solve it for a longer time. Okay. So mathematically, okay, so this is not precisely what I solved, but this is a way to understand how the order of the nonlinearity affects the existent time. Okay, the time the solution remain exists. So I'm just testing the idea of nonlinearity. So I just artificially use this model. I just write down randomly. Okay, so I mean, this is really the nonlinear term is of order p plus 1. Okay, the nonlinear terms of order p plus 1, and that's linear part. And we know that we know this L infinity norm. In other words, the size of the wave is bounded by the energy and with the decay rate. So I built in the decay rate here. So this n is either 2 or 3, right? So we care about 2 or 3 dimensional water wave. 3D is the one that in the real world. We live in 3D, but 2D is a cross section. Okay, okay. So now mathematically, in PDE, the basic philosophy is that we should be able to solve the equation for as long as the energy remains finite, okay? Or we should be able to solve the equation in the space where the solution exists, energy remains finite. So you multiply dTu to both sides of the equation, and then you integrate, and you will find that the left-hand side gives you the derivative of the energy, right? You multiply dTu and integrate, or you take derivative and then multiply it. So that's what you have, all the derivative here. But anyway, basic idea is you multiply dTu and integrate. You get derivative dE dt, right? And the right-hand side, I keep the energy term, so multiply dTu, and I take out dTu to power p, right? So I take out dTu to power p, and I keep the energy. And I know this infinity norm is bounded by this L2 norm, so I just plug in. Okay, so the energy will satisfy this ODE inequality. So I want to understand for how long this energy remains finite. Okay, so I solve this ODE and inequality, and I find that the energy is bounded below by this quantity. So in order to show that this quantity is finite, that means the left-hand side has to be strictly greater than 0. And this will be guaranteed if the right-hand side is strictly greater than 0, right? Right-hand side strictly greater than 0 implies the left-hand side is strictly greater than 0. That means energy has to be strictly less than infinity, right? It has to be finite. If it's infinite, and then 0, okay? Okay, so this means this integral has to be bounded by this one, okay? So now we test what happens. So we plug in different nonlinearity, right? So if p equal to 1, so that means we look at the quadratic nonlinearity, p equal to 1. So for 2D water wave, we plug in n equal to 2. If p is 1, n is 2, we are integrating 1 over 1 square root 1 plus t, right? So we know we cannot, this integral will become infinite when capital T go to infinity. So this cannot be bounded by the right-hand side for all t. So in fact, so if the energy is of size epsilon square, then we can see that this capital, in order for this to hold, the capital T has to be less than a constant divided by epsilon square. Okay, so that means we can, if there is a quadratic nonlinearity in the 2D water wave, then we can only say that the energy remains finite for time less than 1 over epsilon square. So then, or we can solve it for time less than 1 over epsilon square. Then there's still question remains, OK, what happens after 1 over epsilon square, right? So it's not satisfying. But if we can show that there's no quadratic nonlinearity, the nonlinearity is of cubic higher order. That means p is equal to 2 or greater than 2. Then we plug in, with n equal to 2, we are integrating 1 over 1 plus t, right? So that means we're talking about natural logs bounded by that. So we can solve, so this, we have that capital T is less than exponential 1 over epsilon square, exponential to the power 1 over epsilon, right? That's why we are able to solve the 2D case for exponential time, because after we show there's no quadratic nonlinearity, we find the energy remains finite for exponential time, then we can solve for exponential time, okay? Because this really, we are integrating 1 over 1 plus t, if p is 2, or if the nonlinearity is cubic in higher order. So in 3D, we can test the same idea, right? So in 3D, if there is quadratic nonlinearity, so that means if we don't make effort to understand the nature of the nonlinearity, and we just straightforward write it down, there's quadratic nonlinearity, then in 3D, n is 3, you plug in and you find you are integrating 1 over 1 plus t. So even though we don't understand the nature of the nonlinearity better, straightforwardly, we should be able to solve it for exponential time in 3D already, right? But if we are understanding the nature of the nonlinearity better, that means if we say that, we can show that there's no quadratic nonlinearity. That means if p is 2, so at least the nonlinearity is of cubic in high order. So we are integrating 1 over 1 plus t squared. We know that's integrable. And we can solve it for all time as long as the initial energy is small enough, right? Because this integral is finite. It's bounded by anyway. You can just make this number large. Okay. So this is really the idea why we can solve for exponential time for 2D and global time for 3D. Really, that's the outline of proof. But of course, we are in the real, for the real water wave, this is the idea of proof. But for the water wave equation, you have to work on the water wave equation. You have to carry out this idea for the actual water wave equation. Okay, but that's something, okay, we don't have time to talk about. Okay, okay, so so there's another work of for the 3D water wave by German Masmoudi Shatta, and they are able to show that for a different class of smooth and small initial data, and the solution remains small and smooth for all time, and actually it scatters. So their idea is different in that they are actually saying that, okay, so we want to understand whether we can solve the equation for all time. Then I just solve the equation from infinity time, right? So then we go back to initial time. Whatever we can come back to initial time, that's my data. So that they identify a different class. So that's the different method. Then they identify actually a different class of data. that actually go to infinity for all time because they are solving. Really, they are starting from infinity and go back to the initial time. Okay. Okay, and for water wave, actually, there are different ways to study water wave. I mean, this is very classical. For example, you can think about water waves in different scaling region, and you find in a different scaling region, you will see the KdV equation and even a Kp or Bushnick shallow water and a modulation region, right? That's nonlinear Schrodinger equation. So of course, this derivation has existed a long time ago, but it's in a formal way. But in this work, these mathematicians are able to justify these derivations in a rigorous mathematical term. In other words, they are able to show that the phenomena represented by the KdV, nonlinear Schrodinger equation, Kp, Bushnick, etc., are actually observable in the real water wave in the corresponding region. Okay, okay, and there's so singularities is a different matter, right? So of course, there's a lot of study by physicists for singularities, but very little by mathematicians, okay, in rigorous terms. And actually, but it's very, very understood singularity. Okay, so what's the? I mean, this is not very well understood. Okay, actually not understood mostly. Okay, so singularity. So singularities. So okay, so what happens to singularities, right? So we know that singularity is really of great significance in engineering and physics, right? So we know that. I mean, say in applications. But there's very little study to that. So there are some very recent work by mathematicians. So in this work, they showed the existence of so-called splash singularity. So what is splash singularity? So that's the situation. So basically, the result is that saying that it is possible for a smooth interface to become self-intersecting at later time. Or there is a smooth interface that becomes self-intersecting at later time. Okay, so the idea of this proof is that they actually, because if there's no viscosity, the water wave equation is time reversible. So they start from this situation. Okay, it's self-intersecting, and they apply a velocity field, pulling this wave apart. Okay, they pull it apart, and it becomes something non-self-intersecting. As they say, okay, now I have a wave that, and then I go backwards in time, right? So I have a wave now actually becomes self-intersecting. So this is really just an existence result. Okay, there is a smooth wave that becomes self-intersecting. But there's also other point of view by mathematicians that means that, okay, we can also just to say that, well, just to study very rough initial data. So that represents singularity, right? So we try to say that, okay, the wave is well posed. That means if initially the data is rough and rough, and then you can solve the equation. You can continue the solution in a unique way later time in the same class as initial data with the same roughness. But however, this is not too low, right? So they need to, in this very recent work, they are able to show that it's well posed. That means the interface do not need to be very smooth. It's a little bit over C1.5. Okay, so then the solution is the interface remains smooth for C1.5 plus epsilon in the same class. Okay. Okay, so now of course, actually, if you go to the, next to the swimming pool, very often you see things like that, right? But of course, I mean, this photo I took from the internet. I didn't take it myself. And when I show this in my talk, people say this is due to wind, and you don't have wind. Okay. But anyway, I really want to find the photo without wind, but I couldn't find it. But anyway, I just try to make my point is a lot of times we do see kinks in the real fluids, right, in the interface. Kinks. But the kink definitely is not C1.5 or more, right? It's more like Lipschitz. Okay, so there's kink. a lot of times, so it's just imagine, so just pretend there's no wind. Okay, so this is not the right photo, but anyway, so pretend there's no wind. So we look at this photo, and so we want to ask, how do we understand the structure of the singularity here? What is really happening, right? This is definitely not covered by previous work, because in previous work we assume the interface is smooth. Smooth means that really like C2 or more. Okay, and in this, even the very recent work is C1.5 or more. Okay, so that's not really covering this case. But then you can say that okay, then I solved the equation in the Lipschitz class. Okay, so this is Lipschitz, right? But you solved it, but of course such a result doesn't exist. But even if you solve in Lipschitz class, it could be too general, right? Because Lipschitz is more general than what's represented here. There's structures here. It's just not Lipschitz. It's more specific than Lipschitz. So we want to understand what's really going on here. What type of singularity is this? And really, what's the structure here? The structure of the singularity. Okay. So the question we want to understand the following: what are some typical singular behaviors? Really, what are some typical behaviors? Okay. How does it form, and where does it come from? Okay. And what are some basic structures of the singularities? Okay. So now. Okay, so now we want to use the self-similarity. So we know that self-similarity is an important tool in mass physics. For example, in the heat equation, the fundamental solution is self-similar, right? And that's a basic building block of the solutions of the heat equation. And we also know in the nonlinear conservation law, we know that the Riemann solution of the Riemann problem is self-similar, and that's the basic building blocks of the solutions for the hyperbolic conservation laws. Okay. And this has been used a lot in mass physics. Okay. So basically, we know that if in situation where there's no explicit reference length, like the one we are looking at, we neglect the boundary and bottom, okay, and we neglect wind. Say, for example, like there's no boundary effect, there's no external force, okay, and typical in such a situation, because it doesn't matter, I mean, the length scale, I mean, you can say this is 1 unit and you can say this is 1 unit, right? So in these situations, typical phenomena are often self-similar, okay? So these are really the basic waves we are looking at, okay? So in fact, in water wave, I mean, in this book by Scholar, you can find a self-similar solution for the linear water wave equation. Okay, so he just dropped all the nonlinear term, and he can find a self-similar solution. Okay, and in this more recent work, these also built a self-similar solution, but for an approximate water wave equation. So not the exact one. They are not able to find solution for the exact water wave equation, but by dropping certain terms, they find a self-similar solution. Okay. And in the work of Log-Higgins, did a lot of studies for the singularities in water wave. In particular, he also take advantage of self-similarities. But these are numerical works. Okay. Okay. But it remains open that this question, okay, are there self-similar type singularity in water wave? Okay. What are some basic properties? So that's what we want to understand. Okay. So because in the situation we're dealing with, it looks like, I mean, it's the reference scale. I mean, it's no external force and no boundary, right? So it could be really, self-similar phenomena could exist. Okay, so we see whether this is the case. So for the moment, we focus on 2D water wave. So that means we are not really talking about the one we are seeing in the picture, but just cross-section of it. Okay, and because we know that from our experience, if we understand 2D, we can understand 3D afterwards. Okay. Okay, so, but we know that if we want to talk about singularity, we cannot neglect surface tension, because surface tension has smoothing effect, right? So we take back the surface tension, okay? So this is the same Euler equation, incompressible, irrotational, but now there's a surface tension. Sigma is a surface tension parameter, is a constant. This is I, is imaginary part of this. I just write the mean curvature of the surface interface in this form. So there's a surface tension. The pressure from on the interface has to be proportional to the is a mean curvature, right? So that's how the pressure is now. It's not P equal to 0. Okay, so we reintroduce surface tension to the problem. Okay, okay. So this is a fully nonlinear problem with free boundary, where we don't know how to solve it directly. So we have to rewrite it into a form that we know how to solve. Okay, but we know that. So we know that. So this is a basic fact that if the particle was on the interface initially, it remains on the interface for all time. So that means if I just follow how the particle works, then if I just stay on the interface, I will not see the free boundary anymore, right? Because I'm on the interface, I don't see how my bottom, the ground, under my feet works. Okay. So the idea is really just to develop an equation of the interface and then solve that, okay, and to get rid of the free boundary. Okay. So this is interface in Lagrangian coordinates. That means that if I label the particle at initial time alpha, and I label the same particle for all time, okay, alpha, okay. So the same particle alpha for all time. So this is the trajectory of the same particle alpha at time t, okay. So if I take, this is the trajectory of the particle alpha at time t. So if I take derivative to the velocity, so I write in 2D, I use complex variable, okay. Instead of writing x, y, I write x plus I, y. So taking derivative to t, I get velocity. Taking 2 derivative to t, I get acceleration. And then I can rewrite the Euler equation into this form. So this is acceleration, and that's a gravity term. 0 minus g is 0 gi. It's gi, right, in complex form. So acceleration plus gravity, and that's a pressure term. Now I also have to write down the pressure term on the interface in tangential and normal direction. Okay, so I write in tangential and normal component. That's what it writes out. And in the normal component in particular, the coefficient is really proportional to minus dpdn. Okay, so that's pretty easy to figure out. And we have shown this has to be greater than 0 for the problem to be well posed, right? So this is, keep in mind, this is a Taylor sign condition. A is greater than 0. Okay, okay. So that's now that's the equation of the interface now, right? Z represents the equation of the interface, and that's the interface equation, okay? Okay, so now, of course, we also know that the velocity field is divergence and curl equal to 0, so that's a potential flow. So in particular, that's a Cauchy-Riemann equation, or V bar is holomorphic on the fluid domain, okay? So we write down the equation as the following. Okay, so now we want to test what are the similarity laws. So what are the possible similarity laws? So we just say that, okay, if this is a solution, that's a velocity, pressure, and that's interface. Okay, so we check that if there's no gravity, there's no surface tension, so that means there's no reference length at all. Okay, then we find there's a family of similarity laws. Okay, for all s and all lambda positive, these rescaled functions are still solutions. Okay, if there's no gravity and no surface tension. Okay, now if there's a gravity, there's no surface tension, then we have one reference scale, right? Then there's only one similarity law. That means these are solutions only if s equal to 1/2. Okay. Now, if there's no gravity, there's surface tension, then there's another scaling law. Okay, so similarity law holds for s equal to 3/2. So of course, if there's gravity and surface tension, if both gravity and surface tension are there, then there's no similarity loss. Okay, so because there's too many reference scales. Okay, so now of course we at this point we don't know. So singularity. If there's a singularity, is this really due to similarity? Is this really self-similar? If this is self-similar, which scaling law is following, right? Is this really due to gravity? Is it due to surface tension, or it's due to nothing? Okay, something else. Okay, okay. So we have to look at. So now we look at this problem from a different point of view. Okay, so of course at this point we really don't know if there's self-similar type singularity. But we say that assume there is one. Okay, what happens? Say assume there is one. What is going on? Say assume there is self-similar type singularity at time t and at this position alpha equal to 0. So what does that mean? That means if we keep zooming in the singularity, the shape doesn't change, right? That's really, there's a limiting profile. So there's a limiting profile means that we just rescale it, we zoom in, right? We let epsilon go to 0, there should be a limiting profile, okay? So of course, correspondingly, the rescaled, this A is negative dpdn should also go to a limit. And keep in mind this capital A has to be positive, greater than or equal to 0, because this is a limit of negative dpdn, right? Which this guy is positive, okay? The limit of positive is positive, okay, non-negative. Okay, so now we try to understand, okay, so if there's a self-similar solution, a self-similar type of singularity, which scaling law is this following, okay? So we just plug back. Naively, we look at this, okay, so this term is in balance of that if S is equal to 1/2. And of course, if we neglect this one, this term is in balance of that if S is 3/2, right? This is surface tension term, this is gravity term. But which one? It's difficult to say, right? So which one? We don't know, so still. But now we have a limiting profile. We assume that we have a limiting profile. So it's straightforward that to check that the limiting profile has to be self-similar, right? And obey this scaling law. Okay, so this is a limiting profile. It has to come from somewhere, right? It come from some initial time, initial data. So the zt is a velocity, right? This z is a position taking derivative to t is velocity. So that means initial velocity has to be homogeneous of degree 1 minus s. Okay, what does that mean? So this has to behave like alpha to power 1 minus s. Okay, so now we look at this. If s is not 0, if s is not 1, alpha to 1 minus s, that means if alpha is 0, it's either 0 or infinity. If alpha is infinity, it's infinity or 0, right? So in other words, alpha to power 1 minus s has to have some sharp differences at different point of alpha, right? The difference can be between 0 and infinity. So, and we look at this picture. We look at the velocity. So suppose this is really due to self-similar type of singularity. So this actually is a question bothered me for a long time. Which scaling law? So does really the velocity change a lot by a lot at nearby point? At least I couldn't convince myself it should change that much, right? The velocity field, I mean, it should be not so different from point to point, okay? So I kind of think, okay, so maybe this is not right to think about s not equal to 1. The only possibility is s equal to 1. If s equal to 1, then this is homogeneous of degree 0, so this is a constant. So that means initial velocity is more or less homogeneous. It's not varying by a lot, okay? So at least for the moment, I think let's just look at s equal to 1 and see what happens. Whether we can find anything that we can explain, okay, reasonable. Okay, so just say let's s equal to 1. That means we are thinking that initially the velocity field should be not too different from point to point. Okay, and if s equal to 1, we know that this is not due to gravity, not due to surface tension, right? If s equal to 1 is from the s equal to 1, it seems because epsilon small seems this is a negligible term, right? But s equal to 1, it seems this is huge. But however, we do have something here, and this could be small because this is a curvature term, right? The curvature could be, if the wave is very flat, then the curvature is small. So overall, we really don't know if this is big or small, right? So we can only know if this is big or small after we have the profile, okay? So now for the moment, we say that, okay, let me just neglect the surface tension and the gravity. And we just think s equal to 1, and we forget about gravity and surface tension. That means we think there could be a similarity, there could be singularity of self-similar type obeying scaling law s equal to 1. And in that case, neither gravity and the surface tension is in charge. Okay, so that means we now neglect these two terms. Let's try to find the profile. Okay, so neglect these two terms, and we go to the limit. The limiting profile has to satisfy this, right? So this is really the water wave equation, the Euler equation, okay, the Euler equation by taking gravity 0, surface tension 0. Okay, so this is a water wave equation without gravity and surface tension. Okay, and this is the equation the limiting profile has to satisfy. If the singularity is of self-similar type, then the limiting profile has to satisfy this equation for gravity and the surface tension is equal to 0. Okay, so and this is boundary value of a homomorphic function. That means we are talking about incompressible and the irrotational case. Okay, yeah.
How do you get waves if you don't have gravity?
That's true. Yeah, I don't know. Good question. But we are talking about singularities, right? So we want to, because we are really looking at the tip, we are just looking at near singular terms, okay? So we want to say that, well, okay, we don't know if it's due to gravity or not, right? So, I mean, at this, because the waveform, we don't know if it's due to gravity. We don't know if the singularity is due to gravity or not. So for the moment, I just say, let me see what I can find and whether this is anything reasonable. Okay. So the wave is already formed. It's due to gravity. That's true. But the question is whether the singularity is due to gravity. Does that make sense? Okay. 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 So the question is whether the singularity is due to gravity or not. Okay. But for the moment, I mean, I'm a mathematician, right? So I could have. It's a theoretical wave, but I hope it's not. Okay, so I mean, it's nothing interesting if it's theoretical only. So we really, I really hope that the work can explain the real situation. Okay, so yeah, I care about the real situation actually, but for the moment, I mean, you have to make assumptions and you look at what happens and then you try to explain, right, from whether this is anything reasonable. Okay, just by looking at the real phenomena. Okay, so whether it can be explained. Okay, so we just look at the situation. Okay, so this is the equation limiting profile has to satisfy, and we're neglecting the effect of gravity and surface tension. Okay, so this limiting profile it represents the singularity, and we want to say if there is a singularity due to self-similar, following is of self-similar type. So now we want to solve this equation, right? So we want to solve this equation, and we want to see whether we are seeing anything reasonable. And s equal to 1, right? S equal to 1, that's a particular scaling law. We are thinking that it could be reasonable. And of course, this is a greater than or equal to 0 has to be there because this is really the following from the Taylor sign condition. Because if the Taylor sign condition holds, there's bubble, then we don't really talk about singularity because the problem is ill-posed. There's already bubble, right? So we don't think about bubble. So the problem is well-posed, and we want to understand where the singularity is, what the singularities are. Okay, so we just plug in, right? That's the answers you want to plug in. Beta is alpha over t. That's a hyperbolic scaling. Okay, so we just plug in. That's pretty straightforward. This capital A is t minus 1a, so little a has to be greater than or equal to 0. Okay, so plugging, that's straightforward. So keep in mind, u represents acceleration, w is velocity, psi is a wave profile. Okay, a is a Taylor sign condition. Okay, plugging. So we know acceleration is IA times the wave profile. That's what you have, and that's straightforward just by taking derivative. So taking derivative to the first equation and plugging to the second and plugging to the third, and we find that thing. Okay, so we find this is the equation we are solving. Because beta equal to, we have coefficient beta here, so that means we can introduce a jump, right? This is really solving a first order ODE of C prime. So you solve it like this. So B prime is A over beta square, and this A is greater than or equal to 0, right? That's the Taylor sign condition. So that's B prime. So what does that mean? That and we can introduce a jump discontinuity because we have beta equal beta in front, right? This is a weak solution. We can check. It's pretty straightforward. So this means that, what does this mean? This C prime, the wave profile derivative is like this. So this is a phase angle, right? Phase angle, and by far we haven't used incompressible rotational, only the Euler equation and the scaling law S equal to 1. So B has to be increasing, right? Because B prime is non-negative. So B has to be increasing. So this means that if I look at a wave, the angle, the tangential angle has to be increasing. So that means from negative infinity, sorry, I reviewed my graph already. From negative infinity to 0, beta B is increasing, the angle, the tangential angle increasing. So the only way I can draw it is like this, right? Increasing. So this has to be concave up, okay? And then, of course, at beta equal to 0, it turns by degree phi, okay? So go up and turn by degree phi, and then increasing again. So the only way to go is like that. And also concave up, right? This is phi, okay? So for the next, I call this nu pi, okay? This very large angle, I call it mu pi, okay? So that's the shape of the wave. So the shape of the wave is like concave up left, concave up right, okay? Is this really realistic? That's a little bit bothersome, right? Is this really realistic? Because we see wave, I mean, very often we think the wave behind us should be like this and that, right? Like the wave, the surfer sea, right? This is like what we have. So why? I mean, is this really realistic? That's the wave, right? Is this really realistic? Both sides is concave up. So, I mean, this is, we haven't found a wave, right? We are just saying that, okay, if there is a wave not due to gravity, not due to surface tension, and if there is a singularity not due to gravity, not due to surface tension, and following the scaling law S equal to 1, hyperbolic scaling law, it has to look like this, concave up and concave up. Okay. Is there any real wave like this? So at this time, I was invited by friends in San Diego, and that's the photo I took there. From this angle, I actually could see wave coming in. Okay. So we see that the wave coming in from outside and here. So actually, it was a quite nice day, so not so much wind. So we have wave go in, right? So there's a wave train form because the water is going in, right? Wave train form, and this wave train is quite smooth at this moment, okay? And at next moment, and you can see that a kink form, okay? So this kink form, of course, what I can see, my camera is not so good, but of course you're not convinced that both sides is concave up. Okay, so actually I see most of the time the wave is concave up. So let me switch to my notebook. Okay, so and I can enlarge the photograph a little bit. So of course this is the wave train, right? The second wave, I say that both sides is concave up. Of course, from here, it's not convincing. So let me, is this concave up, both sides? It is? Oh, you are still not convinced? Let me make it even larger. Is it concave? No, not really, right? Okay, you can tell me, though, you're lying, but that's okay. Is it concave up? Not.
One side.
Huh?
Only one side.
Only one side. I see. Why? I think both sides are concave up. I want to prove I'm correct. You're saying only one side.
Well, we're not sure the other side.
Which side? Why do you think it's not sure?
Because we don't see it from picture.
Huh?
Because you take a picture from this side, so you can only see
No, but I'm seeing both sides. No, you see this side and that side, right? But usually, of course, you only see wave coming in like this, right? So it's very worrisome because I or never had paid attention previously because I didn't really know what to look at. You look at the wave, you don't know what to look at if you don't understand it, right? So you don't have focus. And now once I figure out that's both sides concave up, I start to worry. I don't remember I ever see wave both sides concave up. Okay, but then I was convinced when I was at that spot. I see a lot of times waves do concave up both sides. Okay, so if you're not convinced, that's okay. But of course, I have to continue. Oops. How do I switch to the PC? Okay, you are not convinced? Okay, so then the next moment, it breaks, right? So wave train forms and then push up, and I find, at least my observation is concave up on both sides and then break. Okay, so this is, the concave up part happens on the deeper part of the ocean, okay, always deeper. And then once it gets closer to the beach, it breaks, okay, like that. Okay, so of course this here I enlarge it and try to tell you this is concave up on both sides, and you are not convinced. That's okay, but I have a better picture next. So of course, so now once I know what to look for, actually so this is a photo that actually I took on a surf webcam, and then it's a surf website. It's a real wave, and this guy definitely has a better camera than I have, and then probably just take right in front of it. It looks concave up, right? Both sides. Okay, that's good. Okay, so both sides are concave up. Okay, and we're happy. And even if I look at this photograph, it looks like concave up a lot of times. But of course, their wind, sometimes it's not so concave up. Okay, but once you know what to look for, you start to realize, yeah, that's not so bad. It's concave up a lot of times. Okay, okay, but still, for the moment, what we are saying is, if it exists, and if it's due to s equal to 1, it's the hyperbolic scaling law, then it has to have concave up both sides. Okay, but we haven't proved it exists, so we have to show actually there's such a wave. If it's not there, then of course everything's in vain, right? It's useless. So we have to prove it exists. So that means we have to solve the equation. Okay, so we solve the equation just using the complex analysis because we're dealing with potential flow. It is holomorphic, right? Velocity field is anti-holomorphic. So we will write down the boundary value of the velocity field, okay? And we use a Riemann mapping, conformal mapping, taking the fluid domain into the lower half plane, okay? So this is a lower half plane, okay? So this I is here, okay? So this is a conformal mapping from this fluid domain to the lower half plane, okay? So lower half plane is like P minus, okay? Okay, so now of course, we can write down the Riemann mapping, right? Because I call this angle nu pi, this angle mu pi. Then, of course, if I is outside, basically this Riemann mapping inverse from the lower half to here, we know we can write down such answers, right? This represents angle at origin. This is represent angle at infinity. And of course, this is not necessarily a bounded function, but I just say that. I mean, actually, this is a nice function. Okay, we don't know how nice it is, but definitely doesn't contain singular part as singular as these two parts. Okay, so we write down the answers for the Riemann mapping. We assume the Riemann mapping take this form. Okay, so plug in. Definitely, you can assume it because it's conformal. Anyway, any Riemann mapping can be like this. Okay. Okay. So now you write down the boundary value of the Riemann mapping, and then you plug in, you calculate, and we find that. So remember, this W bar is boundary value of holomorphic function, right? So if you take derivative to this holomorphic function, it's still holomorphic. And take derivative to the Riemann mapping, of course, the holomorphic function is also holomorphic. So this left-hand side, the product is holomorphic, and its boundary value, its value along the boundary of the lower half plane is this quantity. And if you calculate, it's purely imaginary. So there's no real part. So what does that mean? So we know the basic property. If the holomorphic function, say, is bounded and its boundary value, the real part of its boundary value is 0, then an imaginary part has to be constant, right? That's a basic property. But the problem is we are not looking at bounded holomorphic function. Our holomorphic function has singularities. So in fact, it does have singularities, so that means it's not so straightforward, but we can figure out what it is, okay, just by understanding the singularity. So now we have to make assumption at infinity, but in the real world, because the velocity field satisfies Laplace equation, so we assume that it behaves like the fundamental solution of the Laplace, taking derivative of natural log is 1 over z, right? Natural log is the fundamental solution of the Laplace in 2D. So that's what we have. That we just assume that's decay rate. We also assume that this angle, the tangential angle, do not go over infinite many degrees. So that means the interface should not roll up infinite many times. Of course, I mean, water waves never roll up infinite many times. So that's its derivative integrable. Okay, the angle goes through finite many angles. Okay, so then we have such behavior at origin and infinity. And of course, by getting rid of some essential type of singularity, basically says that we don't think the velocity field should tend to infinity to the origin in exponentially fast. In real situation, velocity never do that, right? So getting rid of this, we don't have many choice. We find that the product of this holomorphic function, by multiplying z, it has to be constant times I. I is square minus I is okay. So square root minus 1, ik. Okay, and kappa has to be positive. Then we can just plug in then we can. I mean, that's pretty straightforward. You just plug in. Okay, so you figure out the equation for the derivative of the angle, tangential angle. It should look like this. And we know the derivative of the tangential angle. We know the tangential angle should not go through infinite many angles, right? So this has to be integrable. In order for this to be integrable, we find, of course, this mu cannot be anything, nu cannot be anything, right? So we find this nu has to be greater than 1/2, mu has to be less than 1/2. So in other words, if there is a singularity due to of self-similar type due to the scaling law s equal to 1, then this angle has to be less than 90 degrees. This angle has to be less than 90 degrees, and this angle has to be greater than 90 degrees. Okay. So if such a singularity exists, both sides has to be concave up, and this angle has to be less than 90. This has to be greater than 90. But still, we haven't really proved such a thing exists, right? So now we have to see whether this exists. Okay, we write down the equation, and we want to solve it. Okay, so that's the equation, and we have to solve it. So the equation to solve it is the following. The first, we have to find a Pauli estimate. So that means we have to see where does this exist. Okay, if it exists, where does it exist? And then we go find it in where it exists. So a Pauli estimate. So we find that indeed, if we assume the wave is symmetric, okay, if we assume it's symmetric, then actually this G has to be bounded and satisfy this property. So this G is this guy here. Okay, so anyway, so probably, and then after that, we are able to prove existence. So that means that in particular, what we prove is there exists a solution such that this is bounded and even and increasing, and this is infinity. So in other words, we show there is a symmetric wave of this type. Okay. So what we can show for the moment is indeed there is a wave, a symmetric wave. Okay. Okay, symmetric wave. So in fact, for any angle less than ½ pi, for any angle bigger than ½ pi, you can find a symmetric wave. So we have a 2-parameter family of symmetric waves. Okay, 1 plus meters mu and 1 nu. Okay. Okay, so that exists. But now for the moment, so we find it. Okay, we find it. But then now we want to understand what does gravity and the surface tension do, right? So now it's easy, right? Once you have the profile, you can just plug in, right? Check out the velocity. That's a surface tension, and you calculate the velocity. And we find that the surface tension is, so remember, the singularity happens at t equal to 0, right? So we only care about t close to 0. So t close to 0, so for a region that's a little bit away from the tip, surface tension is negligible. So in other words, so surface tension is negligible away from the tip, but the surface tension is significant near the tip. So in other words, only the surface tension is important in a small region here, but negligible outside this. Okay, and gravity, in fact, is also not negligible at the tip, but negligible away from it. But this region, this power is greater than this, so it's a smaller region. Okay, so that's the shape of the wave. So this is a symmetric one. And in particular, we can calculate what happens, what is causing it. So you can calculate the velocity, initial velocity. So that basically it says that the initial velocity is pushing down like this in the waveform. Okay. So in fact, I mean, after I solved the problem, I thought, after I look at this, I mean, after existence, I thought, is this really reasonable, right? It seems, if you think about it, right, so if you just, the wave come in, but you move faster than the wave, then, of course, what is front and what's back, right? Front become back, and the back become front. So there shouldn't be the notion front back. Okay, so both sides, I mean, you shouldn't say one side is concave and one side is concave down because it's pushing. It should be like this. Okay, okay. So, but still, this is existence of such wave, but there are a lot of questions to be answered, right? So, in particular, we know that we can see certain phenomena because it's stable. Okay, so it's open that whether this is stable. Okay, such self-similar solution is stable, and of course we have to understand wave interaction, right? So two waves or many waves of this, how do they interact? Because you see the picture, there are many waves of this type, right? They are interacting with each other. How do they interact? Only after we understand wave interaction, we can understand the bed of the wave we are looking at. Okay, so thank you very much. Yeah.
I was wondering about viscosity, how that affects the neighborhood of the tip.
I didn't calculate the viscosity, but that's a good question. I don't know how it affects the tip. But I think that in general, viscosity is important, for example, in a small container, right? But for a wave in such a, I think it's negligible. But then, of course, you still, yeah, it's in the singular case. I don't know. I didn't calculate it. It could be significant.
Small waves, viscosity
yeah.
is quite important.
Yeah, yeah.
Large waves, I was just wondering right at the tip.
Yeah, right at the tip, I don't know. I didn't calculate. Yeah, because everything is really, just, my starting point is no viscosity.
Yeah.
So, yeah.
Wasn't a fair question.
Yeah, not a fair question, because I think, well, for such a big container, the viscosity is negligible from the beginning, right? But now we're talking about tip. It could be important. I don't know. Yeah. Okay.
Any more questions? If not, let's thank our speaker again.